So example 4, finding minimum length. So you are in a rowboat on Lake Erie on vacation, right? 2 miles from from a straight shoreline, taking your potential in-laws on a boat ride. 6 miles down the shoreline from the nearest point on the shore is an outhouse. But we're back in the old days, right? You suddenly feel the need for its use. It's October, so the water is way too cold to go in, and besides, your in-laws are already pretty unimpressed with your yacht, your supposed yacht, which is only a rowboat. It wouldn't help matters to jump over the side to relieve your distended bladder, so that wouldn't look good, right? And also, the shoreline is populated with lots of houses, all owned by people who already have restraining orders against you. So I don't know what you've been up to, but I'm just saying. If you can row at 2 miles per hour and run at 6 miles per hour, which is, by the way, if you didn't have to keep your knees together, you would probably run faster. For what point at the shoreline should you aim in order to minimize the amount of time? So here's what we want to minimize: time, right? Minimize the amount of time it takes you to get to the outhouse. So of course you're going to take out your graphing calculator and calculate that while you're sitting in the rowboat, because you want to spend time on that. Uh, Obviously, I can tell you this is just a funny little story here, so I thought it would make you laugh. But a lot of times this is like, it's also called a pipeline problem. Like you're trying to get a pipe to shore. What would be the optimal time to get natural gas into shore, for example? Should you angle the pipeline and then run it against the shore? Because of the temperatures are so different in the pipes underwater as opposed to on land, it actually changes how fast the gas can go through the pipes at different temperatures. So it's just an interesting, so just to relate this to an actual real life problem. The first thing I would probably draw is a picture of this. So you're out here with your in-laws, potential in-laws, in the rowboat, which is 2 miles from shore, and you have the outhouse over here on the side. And it's just a little side story. I was trying to find a picture of an outhouse, and I got down a rabbit hole about the history of outhouses. So if anybody's interested, I can always tell you about the history of an outhouse in the U.S. So what we need to do is then define some of the pieces. First of all, I know that the distance from the shore where that's perpendicular to the shoreline was 6 miles away, I think it said, right? 6 miles down the shoreline from the nearest point on the shore, right? So 6 miles. And I know that there's two parts. There's going to be part in which we're rowing, that's Y, and a part in which we're running with our knees together to get to the outhouse. So that means I'm going to name that y, those two distances y and x, and that I can then find all the other pieces. You're given the 2, and your 6 minus x would have to be this part of the right triangle. So let's figure out what we're optimizing, which is actually time here. And those things that I drew are distances. So this is where the constraints actually come in and are pretty important, because I have to find first the distance that I'm traveling in the boat is y. So that means I need to then somehow rewrite y in terms of x, and I need to figure out how much time it is. And the reason why I want to rewrite y in terms of x is because I want to figure out, I need to write the time function in just one variable. So I think I'm just going to rewrite everything in terms of x. You could also rewrite everything in terms of y. It just makes it a little more complicated, I would say. All right, so in this particular problem, it's important that we remember that rate times time is equal to distance. So time, which is what we're actually looking for here, we need to keep in mind is distance over time. So y is the distance that we traveled in the boat. So I need to take that distance and divide by the rate at which we row. So that's why the time in the boat, so I called it T sub B for boat, is then equal to whatever the distance is in terms of x of y, or the length of y. And I used Pythagorean theorem to get there, right? Because we have a right triangle over here. That's for this up here is where I used Pythagorean theorem, and I used this triangle that I'm highlighting in blue there to create that, which allowed me to solve for y. And I need to find the time in the boat because I'm optimizing time. So I have to then rewrite all of this in terms of time. So that's where I got, and you're told that it took you could row at 2 miles per hour. So I took the distance, which was y, and divided by the rate to get the time in the boat. And then we have to do the same thing for the distance we're walking or running, right? So the rate at which we could do that, but that's a little simpler. So the time on the shore, t sub s, is equal to x over 6. Now I'm ready to write the optimization function, which is time in this case. So the total time is going to be the time you spent in the boat. That's right here, highlighting. And the time you spent running on the shore. So I'm just adding those two things. And I just put the 1/2 out in front because it would be much easier to put it on in the calculator, which is what we're going to use. This is going to be a calculator problem most likely. And a couple of things I want you to keep in mind. I know that x is either going to be 0. So for example, one option would be to just completely sail directly and spend all of your time in the boat and just sail directly for the outhouse. That would mean x was equal to 0. And the other option is that x is equal to 6. That means that you just row directly to the shore and then run the entire distance along. So those are the two options. It would not make sense to sail in the opposite direction of the outhouse. So that's why you don't have to consider that. And it wouldn't make sense to sail past the outhouse and then run back that way because you're slower in the boat than you are running. So therefore, it is a reasonable endpoints or interval to use is to let x either be 0. That means you're just rowing directly to the outhouse, or let x be 6. That means you're rowing directly to the most direct point on the shore and then start running. Those are the two reasonable endpoints. So that means then I need to find the derivative. Look, here I'm finding the derivative by hand. I'm just telling you right now, most likely this would be a calculator problem. So instead, you would go to the calculator and have it find it for you. So this type of problem is more likely to be on the calculator. Then you would just write down what the calculator told you. It might not look exactly like this. It might look slightly different, but it will give you the same value. And then you will take the calculator. I'm going to show a video, I'll put it underneath here, of how to use the TI-89 to do this particular problem. So then then you do not find the derivative by hand. You're just going to let y1 equal whatever the t function was, right? And then you could actually ask y2 to find the derivative there and plot that if you wanted to, or you could do it in the home screen. There are lots of options there that we can talk about. So if I'm using the calculator to solve for this, I just have to remember to write in my work t prime is equal to 0 when x is equal to, and I asked the calculator to do this, and I also asked it to find it in decimal representation, but you just have to remember, always store value in a variable so that you don't only round at the very end of a problem. Now, in this particular case, it doesn't matter so much, but you just have to keep that in the back of your mind. So now, oh, did I leave something out up here? No, I didn't. All right, so then we're going to test those values. So this one has endpoints. So when it has endpoints, 0 and 6, you got to use EVT, extreme value theorem. So in this particular case, the endpoint happens when x is equal to 0 and another one at 6. So I'm then going to test each of those values and put them into the y1 function and see what these represent time, by the way. So this is the time it takes if x was equal to 0. In other words, if we just rode directly to the outhouse. If it would be t is equal to 2 if we just went directly to the shore. So this is here, this one is the smallest value I get. So my best plan would be you should aim the boat at the point 5.293 miles away from the outhouse along the shoreline. That's really what we're aiming for. And that would give you the minimal amount of time. And then I will try and show you how to actually use some of the features on your calculators.